All right. So, first off, I hope everybody had a wonderful winter break. I know that many of you I know are raring and excited to be here at 8 o'clock in the morning, especially to make the cold trek from engineering to Harris Hall over here. So, but this is going to be, I think, a really a good class, a really exciting class. I don't mean to sound melodramatic when I say this, but I think this is probably one of the most important classes that you'll take as an engineer, and I think you'll understand that as we begin discussing some of the key topics in this course throughout the semester, because I think this is the course that you finally start becoming an engineer. Don't get me wrong, I think statics is critical, but I've been an engineer for a number of years now, and I've never really had any problems where there was a hot air balloon and 3 cables that had to hold it down, and what's the tension in each cable. I mean, those problems are necessary, I think, to understand the principles of statics, and you need to understand the principles of statics to be an engineer. But I think this is where it gets real in this class, is where you actually start, the light bulb starts clicking, you're like, okay, I get it, I'm an engineer now. We are going to be probably a little bit like sardines in here. We were originally going to have this in the engineering building, but we had 52 people in the class, and the largest single classroom had 48 seats, hence why we moved it over here. I wanted to try and get it in Smith Hall again, but it was full, and Corbley 105 was full as well, or it was booked. So this was the next best option. But let's go ahead and get into our logistics. So first off, one of the things I'll mention right off the bat is my my week is a little booked with some things. I have a meeting with various folks Thursday morning, including the university president and whatnot, so I kind of have to be there. I'm going to pre-record the lecture on Thursday and post that to YouTube and whatnot, so we will not meet together at 8 a.m. in 2 days. Okay, everybody okay with that? That'll be pre-recorded and posted to the YouTube playlist and whatnot, and I'll get into some class logistics here in a little bit. If you go to Blackboard, you will see the syllabus for the course posted. That's already been posted and taken care of. For those of you that had me for class last semester, which is the vast majority of you, I don't operate this class really any differently. I mean, we're still going to have, sort of that daily homework assignment thing and whatnot. And I'll talk a little bit about that today because I actually do have a homework for you today due Thursday, but we'll get to that here in a little bit. Let's talk a little bit about the course organization and how the course is operated. So first off, here's the textbook, the Mechanics and Materials textbook by Goodnow and Gear. This textbook has been used for quite some time here at Marshall. In fact, the last time I taught this course was 4 years ago, and we were still using this edition of the book. So if you have a friend, if you haven't purchased it yet, and you have a friend that has it and you want to borrow it, that's completely fine. I don't care if you have a physical version or a digital version, what have you, but I do think it's necessary. I think that you're, at least with this class, you are starting to get into the realm of where the textbooks, I think, start becoming necessary beyond just getting through a given class. I mean, I'm just going to be frank. I got rid of my psychology book when I was in college. I got rid of my history books. I kept my Mechanics and Materials textbook because you're going to use this when you get out of here. And so I'm not saying you have to purchase it or whatnot, but I think you're starting to broach into that realm where they start becoming necessary. In terms of the grade is computed about the same as it is in as it was in statics. There's attendance, homework, and 3 exams. I think in here I placed a little bit more weight on the homework than I did the attendance because I tend to do that as you start with my courses as you start moving forward through the program, because I think you start getting to the point where it's like, you should sort of be expected to be here, but I didn't, soften it crazily. So the attendance is 5%, the homework is 35%, and each of the 3 exams are 20% apiece. I only have 3 exams in here, 2 exams and a final, and I will tell you the final is not comprehensive. Okay, it is not a comprehensive final like it was in statics. This course has a little bit more of a modular nature to it. You learn topics A and B, and then you move on to the next topic, and then you move on to the next topic. And so when you do an exam, you can sort of focus your exams on, given topics. Our first exam is going to focus on the fundamentals of stresses and strains, and then axially loaded members and torsionally loaded shafts. And then once we're done with that, we move on to the next topic. And then once we're done with those topics, we move on to the next one. So I've always said that for those intermediate exams, I don't intend for them to be comprehensive, even though sometimes there's a little bit of material that bleeds over. I think I can definitely deliver it on that in this course, maybe even a little bit more than I could in statics. Let's talk about some technology that we use for the class. How many of you have been on Blackboard yet? It's different, isn't it? Different than it was last semester. Honestly, it's different aesthetically, but it sort of functions the same way. At least it does for me in the background. I don't think it's all that different for you either. I use Blackboard pretty religiously in terms of reporting grades and posting materials. If you look right now, you're going to see the lecture notes for this week are posted. I will tend to post those regularly as the semester progresses. The homework assignments are going to be posted there. The homework solutions are going to be posted there. You will also find a link for the YouTube playlist for the course. I'll talk a little bit about YouTube as well, but if you might notice, I don't know if it was easier to, or difficult to see in Smith Hall 154, but I've got a little lapel mic on right now. I am recording the screen. I'm also recording my voice. This will get posted as a video to the course YouTube playlist, and the link is there on Blackboard. So if you ever miss a class, you can always catch up. I will also tend to do the problems on the screen. Given what's going on today, I may not do the problem today on the screen simply because we don't have this TV out, and there's probably like 30 of you that aren't going to be able to see it, and so I'd rather do it on the board because I know everybody can see it if I do it on the board. But today might be the only day that I do that. In terms of some other technology, if you do not have a cam scanner on your phone, which I think there's some seats over here and whatnot, if you do not have cam scanner or Microsoft Lens or something like that on your phone, I would put that on your phone because we are going to be scanning homework assignments and uploading them to Blackboard. So if you haven't done that yet, I would do that. I also have a little tutorial here in my slides on how to use cam scanner to upload your homework. Yes, sir. We're going to talk about that here in a little bit because the long and short of it is I'm probably going to do the exams a little differently. Honestly, for that regard, we will probably do paper-based exams, and I will probably what I'm leaning on is I'm of the opinion that you shouldn't have to memorize everything, but open book, open notes, and all that stuff with 52 laptops might be difficult. So I might allow you to use a formula sheet and you put whatever you want on it. I tend to also find that method works better from a studying perspective because by making the formula sheet, you're studying. You might not know it, but you're the one who put it all together and whatnot. Okay, I use Microsoft Teams for periodic course announcements. So if you don't have the Teams app on your phone, I'd put it on there. If I need a quick message to send out to the class, I'll do that. If for some reason we're snowed in and we need to do a virtual lecture because of everything going on, I might use Teams to do a live virtual lecture. One thing though that everybody should make sure that they are able to do is access the team for the course. Inside the team for the course, there's a link up top called Class Notebook, and what I will do is do the problems inside the Class Notebook. Again, if we can get the television working today, I'll do the one today in the course notebook. But if not, we'll do this one on the board. But typically what I'll do is do the problems in the course notebook, and you can access them outside of class. If you open up the course notebook, there's a section called Content Library, and you'll see all the stuff I proverbially do on the board inside the team. So you can access that 24 hours a day, 7 days a week. Let's see. The attendance, given the technology today, what I might do is I'll pull the QR code up at the end, and then everybody can come in and scan it. And I'm not going to count anybody late today because of everything going on. But typically, I'll bring up the QR code, you scan it, and I'll post the attendance grades pretty expeditiously. I'm usually pretty good about that. I usually try and ensure that the grades are up to date on Blackboard pretty regularly. The first couple of assignments are actually not PDF upload assignments. There are these, they look like tests on Blackboard, but they're not timed. Basically, you can go in, type in the answers, and it'll grade it for you. So while I'm getting my TA and whatnot set up for the class, we can still make sure that your homework's being graded. And then again, like I said, I will be doing YouTube recordings for all the courses and whatnot. If there's ever an example or whatnot that we might not finish, I might post a quick video kind of going through it. 3 exams in the class. Again, I've spoken about the modular nature of the class and when those exams are. Let me pull up the syllabus. Again, I know that's kind of difficult for everybody to kind of see right now. Let me pull this up real quick. Oh. All right. Let's see. The syllabus, by the way, is on Blackboard, so anybody can download that. If you look at the class, so what I did is I tried to make sure that the exams fell within topics. I think I've found in the past that makes the exams a little easier to do. Your first exam is going to be Tuesday, February 15th. We'll have a review session the Thursday prior, and then we'll come in and do the exam. The second exam is not until after spring break, but it's not the Tuesday after spring break, it's the Thursday after spring break. So that way we're not coming right back from spring break, 8 a.m., boom, you have an exam. But again, I tried to organize the course in such a way that, again, the exams fall along the lines of when we're done with given topics. All right. Any questions about the sort of the course structure, the course layout? Any questions? All right. Okay, so everybody do your best to try and pay attention to this television. Everything good so far? Or?
Yeah, I don't know if it's the power plug. We may have a tripped breaker.
Okay.
Or it may just actually be the TV itself, but I'm going to have to come back after class and troubleshoot a little later.
Okay, all right.
Sorry about that.
No, it's fine, but if you could let me know, I'd appreciate it whenever, you know.
What's your?
Michelson at Marshall, M-I-C-H-A-E-L-S-O-N.
Sorry, I'll let you know.
All right, thank you, I appreciate that. All right. I'm going to try and turn the light off to maybe try and divert a little bit of attention to this television. Again, my apologies for the technical hiccups and whatnot, but I'll walk us through the discussion because this first sort of lecture is just me trying to explain some concepts and get you thinking about what we're doing in here. So I have here 2 objects on the slide, okay? The first object is a soda can, okay? What material is our soda cans typically made out of? Oh, okay, there we go. It's not that early. Everybody knows the answer to that. Now, on the left, I have a soda can, and on the right, I have a solid billet of aluminum. Now, everybody in this room should have the lower arm and grip strength to be able to take an empty soda can and crush it in their hands, right? Can you do that to a solid billet of aluminum? Is anybody from Krypton and have a red S on their chest or anything? Of course not. That's very difficult, okay? Now, why is that? Why is it that something like a soda can is easy to crush, but the solid aluminum billet isn't? What's different? And I'm not asking for a hyper precise answer. I just common sense. Why is it different? Anybody?
Soda cans thinner in their space in between it.
Okay, so you're talking about the geometric definitions, and what were you going to say?
I was going to say you're like moving less material with the top can, like you're squishing less aluminum.
Okay, you're both basically saying the same thing, and I want to add a little bit of precision to it. What we're talking about ultimately is the problem's geometry. Okay, let me give you a mathematical example, and maybe what I will do is draw a little bit on the board here. Let's see if my marker works. Okay, yay, my marker works. Okay, so let's just keep the problem simple. Okay, let's say I have, let's use aluminum since we're in that realm of aluminum. Let's say I have a piece of aluminum and I yank on it. Okay, and let's say I keep on yanking on it. Let's say it's a pretty thin piece of aluminum. And let's say when I get to a load of 100 pounds, that aluminum rod snaps in half. Okay, now let's look at a different scenario. Now let's take a different aluminum rod and let's double the size of that new aluminum rod. How much load do you think it would take to snap the second rod? If I doubled the size? Just basic, relation. What do you think? 200 pounds, right? So what we're talking about here is sort of if we wanted to define this a little more rigorously, what we're saying is that there is a relationship between the response of a given object and its geometric properties, right? Okay, so I want to sort of softly introduce one of the most fundamental terms in this course, which is the concept of stress, okay? I propose that if we're really starting to talk about the behavior and the performance of engineering systems, it's not so much the forces that they're experiencing, it's the stresses. I propose that in this example, if I take an aluminum rod and it takes 100 pounds for it to fail, and if I double the size, it's going to take 200 pounds to fail. It's not the load, and it's not the properties, it's the resulting stress, okay? Now, we use the term stress in this course, and I want to differentiate between a term that you're probably more familiar with. I'm going to be talking about stress. You're probably thinking of pressure, okay? You probably are thinking of pounds per square inch or force per square inch, kilonewton per meter squared, and what have you. And to be clear, they're measured in the same units. Pressures can be in PSI just like stresses can be in PSI. The difference from an engineering perspective is that pressures tend to relate to fluids, to liquids and gases, whereas stresses are for solids and what have you. So I want to make sure that we're differentiating between stresses and pressures right off the bat, because this is a course about stresses. I propose that what stresses are doing they are normalizing the forces that we place on a given element. So instead of dealing with forces, we're dealing with forces per unit area, okay? Now, we have a way of normalizing forces, but we also have a way of normalizing deformations, which is what we'll talk about on Thursday. Would you agree with me that if I wanted to find, let's just say, the volume of this book, okay, that a simple way of computing the volume of this book would be to take the area of this book multiplied by the length? Is that a fair way of looking at it? So if I'm applying force to this book, I can normalize that force by introducing the concept of stress, force per unit area, okay? We have a similar term for normalizing deformation, okay? If I have a rubber band and I apply load to it, it stretches, it gets longer, right? Every single object in this universe, you apply load to it, it deforms, okay? There is no real vibraniums or adamantiums or materials that are infinitely strong. It doesn't work that way, okay? Everything that you apply force to will result in deformation, okay? We can normalize that deformation through this concept strain. Strain is basically deformation per unit length. And so by introducing the concepts of stress and strain, we sort of remove the geometry from the problem so that we can treat the aluminum soda can and the solid aluminum billet in similar fashions because we remove the geometry out of the situation. Because the aluminum soda can has smaller geometric properties such as cross-sectional area, it's going to result in higher stresses under the same force. That's why you can crush a soda can, but you can't for a solid aluminum billet. Does that make sense? Okay, just want to make sure the ideas are in place. Now, let's complicate things a little bit. So I want to sort of illustrate what's going on here on these two images. So first off, what I have here are aluminum rods and wooden dowels. And for the sake of discussion, we're going to assume that their geometrical properties are identical, okay? Same cross-sectional area, same length, same everything. Which do you think is stronger, the aluminum or the wood? I'm asking. What do you think? The aluminum. Now, short answer is that's correct, okay? But my point is, let's talk about what's going on here. I think that I've removed the geometrical issue from this scenario because the geometries are the same. same cross-sectional area, same length, etc., right? So if I take 100 pounds and apply it to the aluminum rod, and 100 pounds and apply it to a wooden dowel, I'm going to get the same stress. But I would argue that the wooden dowel is going to fail first. There's something about the wooden dowel that's just weaker, right? Yes?
If it would bend, like aluminum would bend or metal.
Well, we're gonna talk a little bit about that later on, how alloy type materials like wood will undergo yielding and fracture. Wooden materials will probably split. You know, concretes or ceramics will crack. You know, so on and so forth. Those are very important points. But what I'm just getting at is just, you know, let's just keep a simple example. Like if I had a wooden dowel with me right now, I could probably snap that thing over my knee, right? I couldn't do that for an aluminum rod, right? There's something about that aluminum rod that is stronger, that is tougher, right? There was a video game from the early 90s that has since spawned a number of sequels by the name of Mortal Kombat. Has anybody ever heard of Mortal Kombat? And beyond the main scope of the game, which is just beating the hell out of the opponent, there were these mini games that were in between the fights. Does anybody know what I'm talking about? These were test your mights, right? And what would happen is you would have the controller, and there would be an object that you would need to break, and you would mash the buttons and get the meter up, and then once you hit the trigger, you know, they'd break the object. And the challenges would get harder as the game progressed. Like you'd start off with like wood blocks, and then you'd progress to like, you know, stone and steel and whatnot. But one thing that was kind of interesting was they were all largely the same size. But it got harder as it progressed because there's something about these material properties that make it more difficult. It's easier to fail a wooden dowel than it is an aluminum rod. It's because there's something about the material properties. If I go back to the mathematical perspective, if I take this aluminum rod and I apply 100 pounds to it, but what if I keep all the geometry and the loads the same, but I change the material properties? Does it behave the same? Can it resist more load or less? It's because, well, I don't know. And the reason why is because there's other properties associated with the situation, right? If scenario one deals with the fact that we can remove the geometry from the situation, well, there's more to it than that. We also need to understand the inherent material characteristics. I propose that in this course, not only are we interested in normalizing response by investigating stresses and strains, we are also interested in understanding the relationship between stresses and strains. And I propose that relationship changes dependent upon what material that you look at. For example, and we're going to talk about linear versus nonlinear behavior later, but linear elastic behavior is akin to a rubber band, right? You take the rubber band, you load it, you let it go, it goes back to its original shape. That's elastic behavior, and for the most part, linear behavior as well. I propose that linear relationship, that slope of that curve changes dependent upon what material that you look at. Copper has different properties than aluminum, than steel, than polymers, than ceramics, etc. And so we need to accurately understand those in order to be able to assess engineering systems. How many of you, did any of you do tensile tests in Engineering 215, you mechanical folks? Did you do a tensile test where you took a piece of steel and yanked on it?
Flaws in the material.
Okay.
We did them. They just didn't work right. He sent us pictures of stuff from 5 years ago.
Yep.
Okay. All right. I have a video that I'm gonna pull up a video from week 3. We don't do the testing in here because we do them in other courses. So mechanicals do it in Engineering 215. The civils do it in CE 321. Biomedicals, I'm not sure if and when you do that. I actually don't know. But basically, for our purposes, we're more interested in the math and theory behind utilizing those components later. And it's not just the mathematical properties that we need. We also need to understand the behavior. As we pointed out earlier, wooden materials may split. Alloy materials like metals and whatnot may yield and fracture. Cementitious materials may crack. And so we need to understand those behaviors as well. Let's delve a little bit further. What if I changed the way that I loaded it in general? What if it was the same wooden dowel or the same aluminum rod, and maybe one scenario I stretch it, and maybe another scenario I bend it. Maybe a third scenario I twist it. Would you agree that it's probably going to behave differently under those different conditions? It's going to be able to withstand different loads? That's 100% correct. And so that's actually what we're going to focus a lot of our attention in this course. There are sort of a big four stress formulas that we're going to be deriving throughout the semester, and those are the stress formulas that result from axial load, from a loading along the axis, from torsion, from bending, and from shear. Those are sort of the big four stress formulas that we're going to be dealing with throughout the semester, as well as their resulting deformations. And we're going to see today how the end goal, the end game, if you will, is really prescient on your careers. We've got a couple other things that we're going to be discussing in this course just to kind of illustrate what we're talking about. One of the things that's kind of important, which we'll deal with near the end, is load orientation. If you take an element and you apply it in tension, it tends to elongate. But if you take an element and apply compression to it, it tends to want to do this thing called buckling. Okay? Buckling is very different in terms of its behavior. It's a sudden loss in stiffness. Anything that's in compression, columns, components in machines and systems, very important. Member orientation, stiffness. At one point in statics, we reviewed this thing called a moment of inertia. We're going to spend a lot more time with that in here because it changes response depending upon how a member is loaded. What if you have multiple stresses going on at the same time? What if you have a member that you're loading it, twisting it, bopping it, twisting it? What if you're doing all of this at the same time? What's the worst case stress state? Okay? And ultimately, what you might be asking yourself is, who the hell cares about stresses? Why does this matter? This is going to become very clear today with some of the examples that we're going to look at, because the example that we're going to look at, what we're going to see is why you would care. Why, as an engineer, you would need the concept of stress to be able to assess an engineering system. Okay? So I want to go back to Engineering 213, and again, if it's kind of tough for you over here to see the slides, don't worry. I think I'm going to do this example here on the board today, so it's a little easier for everybody to see. But I want to kind of go back to statics to sort of illustrate some of the ideas that were important to us. One of the most, does anybody remember in statics what our secret weapon was? When we had an engineering system, what was the secret weapon that we developed to determine the internal responses? Remember the samurai sword or the lightsaber, if you happen to be a sci-fi fan? Remember that? Remember, the idea is that if I'm sitting here on the table and you break out the samurai sword or the lightsaber and you cut through the table, that's going to result in a depleted grade on your part, because I'm going to fall and hit the ground and I'm not going to be very happy. Remember that? And the reason why is because the table there are forces inside the table keeping me upright. And so if we're dealing in two-dimensional statics land, there... I thought that was the fire alarm. So 8:30 is the time to wake up for an 8 a.m. class? What's that? Need to update the time zone and whatnot on your phone. So in two-dimensional land, there are at most 3 unknown responses inside a given element. There's the force in the x direction, the force in the y direction, and the resulting moment. Okay? So I propose with each of those loads, we can develop a resulting corresponding stress. And that's in 2D land. If we were going in 3D land, we could get 3 resulting components. We would have the axial force, the torsion, the shears and moments in each direction, etc. And for each of those components, we can develop a resulting associated stress formula. We're going to begin with the most basic of stress formulas that we could deal with in this course, and those are axial stresses. And so I'm going to turn the light on here, because I think at this point I want everybody to kind of see what I'm talking about here. Oh my, that's bright. So the most fundamental stress formula that we will be dealing with in here is axial stress. And the formula for axial stress is P over A, okay? And so where this formula comes from is if I take an element and I apply an axial load to it, a load along its axis, I either stretch it or push it, that I propose that the resulting stress is defined as the load per unit area, okay? Now there are a couple of components that you need to be aware of. This is technically a little bit of a simplification of how this would really be defined, because the way that we would rigorously define this mathematically is we would look at a given differential element of area and say that the stress for that little differential element of area is the force per area, and then we would, if we wanted to rigorously get our stress, we would set that term as the area approaches zero. So we would take the limit of that as the area approaches zero. Don't worry, we're not breaking out any limits or anything in Engineering 216. I just need you to kind of understand that ultimately what we're dealing with is an average stress. And for most cases, an average stress is more than appropriate enough for the purposes of design. Now, let's just talk a little bit about units, okay? In mechanics of deformable bodies, I've got civil engineers and mechanical engineers in the room, and I think it's important that you understand how to navigate both unit systems. So in USCS units, we will tend to deal with either PSI, pounds per square inch, or KSI, kips per square inch, okay? In statics, we introduced the concept of a kip, and that a kip is just 1,000 pounds. In metric, we will be dealing with, essentially newtons per meter squared. The abbreviation for that is a Pascal. One shorthand that I want everybody in here to understand is a kilonewton per millimeter squared is a gigapascal, okay? That's a shorthand that I kind of want you to sort of memorize, because there's going to be problems where they say, okay, the limiting stress is megapascals, and everything is in kilonewtons and millimeters. Take that megapascals, convert it to a gigapascals. It'll make your life a lot easier, okay? So, and we'll have some examples where we go through that relatively shortly. Any questions? All right. I think the easiest way to start introducing the concept of stress from a rigor perspective is to just do some problems, okay? And so I want to talk a little bit about this problem, and I'm probably going to draw a little bit of it up here on the board to make sure that we can all kind of see what's going on here. I have here a two-tiered pipe system, okay? So what I've got here is I've got a pipe, and I've got sort of a pipe welded to that, okay? Now in this system, I've got two different loads applied to these given pipes. So we'll call this PA, and we've got right here, we'll call this PB. We'll do that. And I've got a series of numerical properties for the pipes that we'll deal with here in a bit. But what I'm going to ask is to determine some stress conditions under changing loads. So I'll say, what's the stress if the load is this? What's the load need to be for the stresses to be equal, et cetera, okay? So let's take this problem one step at a time, and let's see what we can ascertain from this. Now, hopefully everybody brought their Casio FX115 ES Plus or similar scientific calculator. I know you're like, day one? Are you kidding me? Yes, we're going to do this on day one. Now, for the sake of keeping this simple, we'll call this pipe 1 and pipe 2. I guess I'm going to have to bring a marker in here because this marker sucks. So, actually, if you've got one, I'm not going to say no. I didn't. That was bad. No, that was bad on my part. Let's see. There we go. That's a lot better. There we go. Thank you. I'll give it back to you. All right. So let's talk about pipe 1. Okay. So for pipe 1, we know that the outside diameter is 2 inches, or sorry, what is it? 2.375 inches. And The inner diameter is 2 inches. Now, if stress is defined as P over A, it's probably a good idea to go ahead and compute the area, right? Now, I'm going to hit you with a little bit of a dose of reality, because I'm all about that in engineering land. What is the area of a circle? How do you compute the area of a circle? How did math professors teach you how to compute the area of a circle? Pi r squared. Okay? Now, I would like you, as a side homework assignment, to go to Lowe's and ask for a 1-inch radius pipe. You're chuckling. What's that?
2-inch pipe.
Why'd you say that? Because that's what they're referred to as, right? Exactly. In the real world, we reference bolts, pipes, threaded rods, etc. in diameters, right? That's just the truth, okay? So what I'll say here is, note the area of a circle is pi r squared, but it's also pi d squared over 4. That's the truth, right? And I'm going to tell you, I'm probably going to start using a lot of formulas in this course referencing diameters. And I'm sure that there is a math professor out there that's going to yell at me and go, mathematically, I get that it is convenient to express circular terms with the radius because it makes the derivation a lot easier. But we're engineers and we're in applied land. And I'm telling you, pipes, bolts, etc., they're referred to in diameters. So let me ask you a question. With that, how do you think that we can determine the area of pipe 1? What do you think would be a formula that we should use? Okay, and what I mean by that is this. Okay, here is the pipe. Okay, and what we're interested in is the area. We're interested in sort of that shaded region. And we've got a scenario where this is the outer diameter. I'll do that. And this is the inner diameter. What is a way that we can determine the area of that pipe? How would we do that?
Use half of the difference in the two as the radius.
Well, hold on. I think you might be overcomplicating it. Hold on.
Do the area with both diameters and subtract each other?
Exactly. In other words, what we can say is the area of the big circle minus the area of the little circle. You see what I'm saying? So I propose, well, here, I'll just leave that up there. I propose that the area of a pipe is pi over 4 times the outer squared minus the inner squared. Just take the difference. Is everybody okay with that? Everybody good with that? Any questions? Okay. So if we're going back to pipe 1, the area of pipe 1 is pi over 4 times, actually, let's use some brackets there. So the outer diameter is 2 3/8 minus 2 inches squared. What is the area of pipe 1? Somebody give me that. We'll say like 3 decimal places.
1.289.
Do I have a second on that? You never had me for class before. I tend to ask for seconds to make sure we all get the same thing. Everybody good? Okay, all right. So for pipe 2, and if you can't read anything, don't hesitate to go. Your handwriting is atrocious, Dr. Mike. Please fix that. we have an outer diameter and an inner diameter, and I'm going to have to read that from the screen here because, again, the lighting and all that. So the outer diameter is, let's see, 2.5 inches, and the inner diameter is 2.25 inches. Can somebody tell me what the area of pipe 2 is going to be? Can somebody do that math, or do I need to chug that out? And don't worry, I'm going to summarize everything over here in a little bit. Anybody got an answer for me?
0.933.
0.933. Do I have a second on that?
Yes.
Okay, all right. Okay, all right. So one of the things I do want to sort of prepare you for in the world of mechanics of deformable bodies is that a lot of times there's some introductory work necessary just computing the properties, like the area, the moment of inertia, just as there might be some introductory work in doing the static equilibrium analysis. Then you can actually sort of get to the crux of the mechanics of deformable bodies. That's just sort of the nature of the beast with the material. So let me sort of summarize where we're at so far. Okay? All right. So here's our scenario. I'm going to sort of redraw it right here. Okay. With this pipe right here, the area is 1.289 inches squared. And this pipe right here, the area is 0.933. So far, so good? Now, we know that that's not the end of the story in terms of the forces applied, because we need to determine stresses. Now, this pipe system has a PA and PB load applied in these particular points. Now, let's go back to statics land. Let's see if you all can remember this. What's that reaction? PA plus PB. Right? Because I got PA down, PB down, I got to have PB going up. Is that okay? All right. Now, I want to ask you, let's go back to static slam. How much force is inside pipe 2? How much force is being carried inside this pipe? Well, what's our secret weapon?
Cross-section.
All right, so samurai sword or lightsaber, right? Which way do you want to look, down or up? Which way has less going on? Down. There we go. Y'all remember this stuff. There we go. So if we look down, we have PB going down, so what's going up? PB. You remember this, right? Remember static equilibrium, right? So I propose the force inside this second pipe is PB, right? Now, I'm just curious if anybody can think this out. What's the force inside pipe 1? Is it PA? What do you think? Is everybody following along with me? If you're not, don't hesitate. There you go. That's exactly right. So here's the deal, okay? Here's the deal. So I've got, let's put some numbers on this, right? Here's a pipe system, right? I've got 100 pounds at the bottom. So I propose that lower pipe is only holding, let's say, 100 pounds. But if I stack 200 pounds right here, that upper pipe's got to hold all that up, right? Make sense? Right? If I'm holding a rope and I'm at the very, very top and I've got two separate people hanging on that rope, I've got to hold up the weight of both of those people. Does that make sense? So I propose, here's what I propose. We need to determine the force in pipe 1 and the force in pipe 2. I propose the force in pipe 2 is PB. The force in pipe 1 is both of those. Does that make sense? Is everybody okay with that? Okay, here's what I'm getting at. We've got areas for both of these pipes, and we have forces in both of these pipes. Now we can start looking at stresses. And if you're still sort of like, I don't see the point, I don't see the end game, watch this. Okay, so let's go back to our problem and let's look at these scenarios. So I want to look at each of these too. So the following scenarios. Determine PB such that the stress in the upper pipe is 2100 psi. So here's what's going on with scenario 1. With scenario 1, we are given that PA is 1750 pounds, and we need to determine PB. And we need to determine PB such that the stress in that first pipe is 2100 psi. Now, I actually think from a mathematical perspective, this is a pretty easy problem. Let me ask you a question. How would you compute the stress in a given pipe? Well, you would take the force in that pipe divided by the area of that pipe, right? So what is the force in that pipe? It's PA plus PB divided by A1. Well, let's take a look at this. What is sigma 1? Sigma 1 is 2100 psi, 1750 pounds plus, I can do better on that, 1750 pounds plus PB divided by 1.289. I mean, if I'm going too fast, don't stop me. Again, you all had me, most of you have had me for class before. If you're confused or if there's anything that you're not following, stop me and tell me what the heck are you talking about. Is everybody kind of following with what I'm doing so far? So I want to figure out how much load will cause 2100 psi in the first pipe. Okay? So 2100 psi is force over area. I'm solving for the load. So how do I solve for the load? What do I do? Multiply both sides by the area. And then what do I do? Just subtract 1750? What is PB in that instance?
956.9.
Say it again? 956.9 pounds. Do I have a second on that? Okay, all right. So let's take a step back because I'm all about making sure we understand the context. So here was the scenario, okay? And the challenge was determine the load that will cause 2100 psi. And this problem is a perfect example of a lot of the things that we do in this class, because before we actually got to the problem, it was like, okay, we need to compute some areas, and then we need to do some static analysis to get some forces, etc. Once we get the forces in the areas, it's actually pretty straightforward. But I'm just going to set the stage right off the bat. There's a lot of times with these courses or with these types of problems, there's background work that you got to do before you get to it, okay? Does that make sense? Now, I could go ahead and jump to the second problem, but I want to look at this scenario a little bit. Let's look at this a little bit. Let me make sure this is clear. I'm just looking at this over here. So in this scenario, we know sigma 1 is 2100 psi. This was not asked in the problem, by the way. This was not asked. But I want to ask you, what is sigma 2? How would you compute sigma 2? I'm asking you. Well, it'd be the force in pipe 2 divided by the area of pipe 2, right? What is the force in pipe 2? It's PB. So PB over A2. We just got PB, right? 956.9 pounds over area 2. Area 2 is 0.933 inches squared. What is that? What is that? What do I got? Say it again. So sigma 2 is 1025.6 psi. Right? Do I have a second on that?
Yep.
All right. I want to talk about these two numbers. And I want to talk about these two numbers with the context that these two pipes are assumed, we'll assume, are made of the same material. Should I have a problem with these numbers? Let's think about this a little bit. I got a two-pipe system. I want to think about this like an engineer, okay? I've got a two-pipe system. I've got a load on this pipe and a load on this pipe. Now I want to think about the aluminum can example. The solid billet and the aluminum can. But they may fail under different loads, but they fail under the same stress. Should I have a problem with these two numbers as an engineer? Why? You're shaking your head yes.
It just seems like they should have equal stress.
Okay, all right, they should be equal. Let's consider something. Let's consider something. Let's say I told you that the allowable stress, the maximum stress that you could put on this pipe or this pipe system before it fails is 1,000 psi. Now, what are you thinking in terms of engineers? Tell me what you think about pipe 2. Is pipe 2 good to go? Is pipe 1 good to go? They're going to fail, right? So, why? The stresses are larger than what they can withstand. So what does that mean for you as an engineer? If I told you the allowable stress on this pipe system was 1,000 psi, let me ask it this way. Let me ask it this way. Here's the pipe system, here's the pipe system, and here's your puppy. Let me ask it that way. If I said that sigma allowable was 1,000 psi, what does that mean? Hold on. Wait. Say that again. Well, I'll be. That's 100% right. This is what we're talking about here. I want you to think about this in terms of an engineer. I'm telling you that if sigma allowable was 1,000 psi, puppy's not having a good day. How do you fix it? You need to change the geometry, right? I'm saying that as an engineer, it tells you you need to select a different pipe. Make sense? Is everybody okay with that? Okay. Now, let's consider a different number. What does that number tell you? What if it's 2,200 psi? All right, hold on. Say that again. Say it louder.
You're okay, but you're pushing it to the top.
Okay, so you're saying that we're both safe, but this is kind of close. So you're almost thinking we need a factor of safety. Maybe that's something we should talk about later this semester, is what's the factor of safety that we should be employing. Maybe there is a difference. What's that?
Is that like a title of a chapter or something?
Well, it's going to be a concept we bring up a little bit later. There is a so to clarify what we mean in terms of factor of safety, and so that I'm being specific, I propose that no, we do not need a factor of safety, and let me explain why. There is a difference between what I'm calling sigma allowable and sigma ultimate. And the difference is what we'll basically say is the factor of safety. So to give you an example, just bear with me. So in Engineering 215, you watched a video of a piece of steel getting snapped in half, right?
No,
And,
you got a picture of it.
okay, you got a picture of it. Well, you were going to watch it, and then the alarm went off. That's what happened, right? Couldn't help it. All right, so what you generate from that is what's called a stress-strain curve. We're going to talk about stress-strain curves a little later. I propose that what you as an engineer can do is you can back off those maximum stresses to generate a sigma allowable. So maybe you use a factor of safety of 2. Take your maximum stress, cut it in half. Boom, we'll use that for sigma allowable. Okay? Now, so assuming factors of safety have been accounted for in these numbers, are we good on this pipe for this second number? What do you say about this pipe? What does the engineer say about that other pipe?
You're not putting enough force on it.
That's another way of looking at it. That's one way of looking at it. What's the other way of looking at it?
It's overbuilt. You don't need one that strong.
It's too expensive. Too much money, right? Why use a pipe that big, right? Why use Schedule 80 when I can use Schedule 40, right? This is what I'm talking about here. This is the point that I was mentioning at the beginning of class, where this is like where it begins, where real engineering begins, where you can look at a system, think about the proverbial puppy, and also think about the bill at the end of the day and start making some decisions, okay? Engineers walk a tightrope between safety and economy. We must produce systems that are safe, but then we also have clients to serve, and we must produce efficient and economical systems as well. If we weren't worried about efficiency and economy, we really wouldn't need engineers. We would just build disastrously large and over-designed engineering systems, and we wouldn't really need to do any math. We just build everything stout, right? And then we wouldn't be able to afford anything. That's kind of the point of why you all are here, right? Does that make sense? So this is sort of the point as to why these stress terms and whatnot are important, okay? And so I kind of wanted to throw some numbers at you so that you could kind of see the end picture. You could see what it's like at the end of the day. All right. Now we're not done with this problem. I got something else I want to look at, because you had mentioned something else. You said that not only if we look at this second number, we could say that this pipe is over-designed, but we could also say that the forces aren't right. Maybe we could balance out the forces a little bit. So let's look at that. Let's see if we can do that. Can I erase a little bit over here? Does everybody have this stuff written down? Okay. All right. So now let's look at scenario 2. So scenario 2, first off, let's rewrite some properties. Let's make sure we have all that. So A1 is, what was that, 1.289. A2 is 0.933. Okay? P1 is still 1,750 pounds. Okay? And I'm looking for P2. Again, I'm still trying to figure out, PA. Sorry, that's incorrectly labeled. That's PA and PB. But specifically, I want to find PB such that the stresses are equal. Because wouldn't that be maybe what we're most interested in? If stress is the normalizing concept, then maybe what I want to do is determine the load such that the stresses are equal. Because that's really what's going to make the behavior uniform. Right? So what's going on there? Okay? What's the deal with sigma 1 equals sigma 2? Okay? What is sigma 2? Sigma 2 is PB over A2, PA plus PB, PB. Over A1. Uh-oh, we're in algebra land. We got to break out those Math 127 skills. So what am I trying to solve for? PB? So how do we do this in algebra land? Maybe we should cross multiply, right? So PA plus PB, why do I keep writing the B? PB times A2 is PB times A1. Carry this through. PA A2 plus PB A2 equals PB A1, right? Get everything, here, let me start writing this up here. Get everything associated with PB on one side of the equal mark. So PA A2 is PB A1 minus PB A2, right? Just subtract that over on the other side. Factor out the PB. You see what I'm doing here? And then I'm dividing. What do you think? Did I do that too fast, or is that okay? Everybody good? So let's plug and chug a little bit. PA is 1,750 pounds. A2, 0.933 over the difference. Do my units work out? That's a check to see whether or not your algebra is done correctly, because I got pounds times inches squared divided by inches squared. The inches squared cancel. What do I get for PB? 4586.4. Do I have a second on that? All right. So if I put that much load here at the bottom, I will get the same stress in pipe 1 as I do in pipe 2. Could we check that? We could very easily check that. We could say, here's the stress formula for sigma 1, here's the stress formula for sigma 2, plug in PB and see if we get the same answer. Let's do that. So let's check. So sigma 1 is PA plus PB over A1. And this is 1.289. What do we get for that? $49.15.7.
Yeah.
Do I have a second on that? Okay. And then sigma 2 is just PB over A2, which is 4586.2 over what? Oh, yeah. Thank you. And then this is 933. What do we get? I think I can probably sort of eyeball that and see it's going to be pretty close.
4915.8.
And so I would propose that's just rounding.
Yeah, because it was like 4915.74 and this one's 4915.755.
Yeah, that's just rounding errors and whatnot, which if we were doing it in Excel or something would be good. What do you think? Let me ask you a question, because for those of you, and anybody can answer, but I'll pose this to those of you that were primarily in statics. Would you prefer I do problems here on the board or on the notebook? I'm asking. What does everybody else think? Because here it's not on the recording or in the notebook, but I think with the room it might be a little easier. I don't care either way.
I'd say the notebook.
All right, let's do this. So Thursday we're not going to have class, so that problem I'm definitely doing on the notebook. Let's see if they get the TV fixed, and we'll take it from there. Because I know for you all, you probably wouldn't know what was going on without that. So maybe if we have the TV fixed and then we shut the door and the lights out, it might be a lot easier to see. But let me back up a little bit and just make sure. Did everybody kind of understand what we're talking about today? Did this concept kind of make sense? The idea of stress and how it leads to what to me what's most important is that you understand that it leads to engineering decisions with the puppy or with the wallet. Okay? Now, what we have yet to discuss is the normalization of deformation. Okay? This is the normalization of force. When you apply force, we don't care about the force so much as the resulting stresses when we're looking at performance. Now we need to look at the resulting strains, which is our discussion point of Thursday's lecture, which will be online. I have something I do need to mention for next Tuesday's homework. So when we come back in person next week, we are going to discuss stress-strain relationships, okay? And what that is going to mean for that resulting assignment is plotting things in Excel, okay? So if you want to bring a laptop, might not be the worst idea in the world for the next course, because we're going to put some things in Excel and plot some data and whatnot. Because I'm going to give you a data set and have you plot the stress-strain curve and determine some requisite values that we would need for mechanics of materials. Sound good? I know it's at 8 in the morning. Yes. Yeah, I'll pull that up here in a second. I know it's 8 in the morning, but I think we're going to have fun this semester. I'm going to pull up the attendance QR code. I'm not going to count anybody late, but if you could sign that, I'd appreciate it. And that's all I have, everybody. I will see you all next week.